You know how we all learned about the seasons in school? Well, what if I told you that a scientific paper is arguing that the whole explanation has a fundamental geometric flaw? Today, we're digging into a really fascinating analysis that uses first principles logic to question the textbook model of Earth's orbit. The author claims there's a major contradiction hiding in plain sight. So let's get into it.
It all kicks off with a simple question, right? One we think we all know the answer to. We watch the seasons change like clockwork every year, but what's really going on up there that drives that cycle? You probably have a picture in your head from your old science class.
And yep, there it is, the classic explanation. We're told Earth is tilted on its axis, about 23.4 degrees, and that this tilt stays locked in the same direction as we go around the sun. So for part of the year, the northern hemisphere is leaning towards the sun, that's our summer, and then later it's leaning away, and that's winter. Simple, makes sense. Or does it?
Well, this is where the paper we're looking at really puts that simple model under the microscope and asks a pretty bold question. Okay, the story sounds good, but is it actually consistent? Geometrically and physically, does the idea of a fixed, tilted axis actually work out when you do the math?
This brings us to the paper's first big challenge. It's all about the geometry of this so-called unchanging axis. See, the author points out a kind of puzzle. How can the axis be fixed in space while also having a very specific and very different alignment with the sun at key points in the year? Let's break down the logic here.
First, we've got to get one key term straight, the terminator. And no, not the Arnold Schwarzenegger kind. In astronomy, the terminator is just the line between day and night on a planet. And here's the crucial part. Because sunlight comes in straight lines, that day/night line is always perpendicular, at a 90-degree angle to the sunlight. Remember that. It's a huge piece of this puzzle.
Okay, so here's where the paper claims things get contradictory. The standard model makes two big claims at once. Claim 1, Earth's axis is fixed, always pointing at the North Star. Got it. But Claim 2 says that at the solstices, that same axis is perfectly parallel to the terminator, the day-night line. The core argument of this paper is that from a purely geometric standpoint, you just can't have both.
To help us wrap our heads around this, the paper gives us a great analogy. Just picture a spinning top on a table. The top is tilted, right? That's the Earth and its tilted axis. The flat surface of the table is the plane of Earth's orbit. And in the middle of the table, you've got a lamp, which is the sun.
So let's use that image and walk through the logic. The spinning top is tilted, and its axis is fixed. It's always pointing to the exact same spot on the ceiling. Now, as that top circles the lamp, the paper asks, can that fixed tilted axis suddenly become perfectly vertical? Perfectly perpendicular to the table, twice during its trip around the lamp? The paper's analysis says absolutely not. For that to happen, some outside force would have to literally grab the top and twist it into that new position.
And the paper even puts a number on it. It calculates that for the axis to hit that perfect alignment we see at the solstices, it would have to physically reorient itself by a full 23.4 degrees, and it would have to do that twice a year. We're not talking about a tiny wobble here. That's a massive shift that just doesn't jive with the whole idea of a fixed axis.
And this leads to the paper's pretty blunt conclusion on the matter. The author states that the two ideas, a fixed axis and the alignment we need for solstices, are just incompatible. It's called a direct geometric impossibility unless you invent some mysterious unphysical force that's twisting our planet around twice a year.
Okay, so that's the geometric argument. But what about the physics? What about the forces involved, like gravity? Well, the paper's second major point moves from pure geometry to dynamics, and it questions the way we usually talk about gravity's effect on our orbit.
Now here's something we know for sure. Earth's orbit isn't a perfect circle. It's a slight ellipse. And because of that, our speed changes. We move fastest when we're closest to the sun, that's called perihelion, and we move slowest when we're farthest away, at aphelion. The question is, why? The paper really takes aim at the common story we're told to explain this speed change. You know, the idea that as Earth falls closer to the sun, gravity gives it a boost and accelerates it, and then as it moves away, gravity acts like a brake. The author argues that this is a complete mischaracterization of how gravity actually works in an orbit.
And this is the key difference. The popular narrative makes it sound like gravity is giving Earth a little push from behind to speed it up. But the paper argues, no, that's not it at all. Gravity is a purely central force. It only pulls straight toward the center of the sun. The change in speed isn't caused by a push or a pull, it's just what happens naturally when you conserve energy and momentum along an elliptical path. It's a geometric consequence.
Here's another really good analogy from the paper to make this clear. Imagine a ball rolling on a frictionless elliptical track that goes around a hill. Gravity is only ever pulling the ball straight down towards the middle of the hill. But just because of the shape of the track, the ball is naturally going to speed up on the steep parts and slow down on the shallower parts. There's no separate force pushing it forward. The speed change is just built into the path itself.
So, after laying out these two big arguments, one about geometry and one about gravity, the paper ties it all together by claiming that the standard model relies on some classic logical fallacies.
The first one is a mouthful, petitio principii, but you probably know it as begging the question. This is basically a form of circular reasoning. It's when you build your argument on an assumption that the thing you're trying to prove is already true.
And the paper argues this is exactly what's happening with the Earth's axis problem. The standard model basically says the fixed tilt causes seasons because it lines up perfectly at the solstices, but it never actually proves that a fixed axis can make those alignments in the first place. It's assuming the conclusion, that it's possible, right in the premise.
The second fallacy the paper points to is false cause. This is the old classic, correlation does not equal causation. Just because two things happen in a sequence doesn't automatically mean the first one caused the second. And according to this analysis, that's the mistake in the gravity explanation. Saying that a push-pull from gravity causes the speed change is a false cause. The paper argues the real cause is the built-in geometry of an elliptical orbit. The speed change is an effect of the path, not an independent action of gravity.
Okay, deep breath. So if we follow the paper's logic, what does all this mean? Why should we care? Well, the author suggests the implications go way beyond just tweaking a textbook diagram.
The paper lays out a few key takeaways. First, that our common diagrams can actually be really misleading. Second, that when we oversimplify science for popular explanations, we can sometimes hide the real physics. But the bigger points are about how we do science. The author stresses that our models of the cosmos should be built from the ground up on solid logic. And crucially, if we find a logical contradiction, we shouldn't ignore it. It should be a giant flashing sign that tells us to go back and re-examine our assumptions.
And that really gets to the core message of this whole analysis. The author is making a pretty strong case that logic and geometry have to come first. If a mathematical proof shows an inconsistency, that should matter more than a story we've been telling for a long time, no matter how comfortable or widely accepted that story is.
And that really leaves us with a final big question to think about. Now, we're not here to declare this paper right or wrong, but the analysis makes you think, doesn't it? If a model this fundamental, something we all learn as kids, could have these kinds of logical inconsistencies, what does that tell us about science itself? And more importantly, what does it tell us about how crucial it is to always be willing to question the things we think we know for sure?